Numerical models combine the knowledge we have of how the world works with the awesome power of computers. They allow us to see into possible futures for all sorts of things: the weather, climate, flooding, economies, farming. Too many to go into here, but they help us plan and prepare for those futures. But those predictions that they give us can end up being chaotic, and this chaos is caused by two little critters, the butterfly and the hawkmoth. What are the butterfly and the hawkmoth, and how do we catch them? Hi, I'm Dr. Chris Skinner, a floodologist, and this is Model Life. Models can be really useful to us, but they can never be right. It is important that we understand all the ways that they might be wrong if we're going to make the best use of them. We need to know when we can trust them and when we can't. The models we use are made up of equations. These are mathematical rules about how the world works. But these rules can only ever be a simplification of that immense complexity of the natural world around us. And the rules we use are usually deterministic. This means that we assume that that rule is correct and capturing all that complexity, and there's no randomness within it, or perceived randomness. It assumes there is one true answer. A model that is constructed using deterministic rules should give you the same answer every time you run that model with the same set of data. However, some elements of the natural world are so complex that they seem fundamentally chaotic. Take the weather and sediment transport. Trying to understand these from just one single model is likely to lead to failure. Looking at you, Michael Fish. One of the biggest problems that causes this is the butterfly. To demonstrate this, I built an experimental flume using the landscape evolution model Caesar Liz flood. This flume is going to simulate the flow of water over the surface and how that induces the geomorphology processes of erosion and deposition, and how those create and change rivers. In my virtual flume, water is poured in from the top and there is a slope which goes slowly down towards the bottom. As the flows scour the surface, they allow water to converge and carve out a channel, and this further concentrates water into that channel and causes even more erosion to occur. Over time, the channel shifts and meanders and avulses into new channels. And this is all based on deterministic rules. If I ran this model 100 times with this set of data, the flume would look the same every single time. However, if I did this test 100 times using a real flume, like the sort you might find at a science festival, I would have 100 different looking rivers at the end. Meteorologist Edward Lorenz described the butterfly effect as part of chaos theory. The idea of the butterfly effect is that within a large and complex system like the Earth's atmosphere, a fundamentally small act, like a butterfly flapping its wings, sets in motion a chain of events. Those small perturbations build up over time, over weeks and weeks and weeks, can eventually influence something much larger and a much further distance away, such as the formation of storms. I introduced a small butterfly into my flume by changing just 1 pixel of height, one little square of elevation in my model, by just 10 centimeters. Watch the difference it makes to the flume on the right compared to the original flume on the left. In our models, butterflies are uncertainties about our initial conditions, things we just cannot know about the data we use to start our models with. An example of this might arise from the precision and the accuracy of the instruments we use to measure the Earth. The airborne laser scanners that we use to measure the Earth's surface can do this to a precision of several millimeters. However, those measurements can also contain errors in the order of 10 to 20 centimeters. We can begin to understand the impact of these uncertainties better by running the model lots of times with different sets of initial data. Each one is equally possible based on what we know. Each one of these sets of initial conditions introduces small perturbations to the model. These perturbations are probably imperceptible when the model begins and during its early stages, but the further we go into the future, the bigger those differences become. We can look then at the spread of all those outputs, this is called an ensemble, and use them to understand the likelihood of different possible futures. This is called probabilistic forecasting. Now let's introduce a Hawkmoth. The Hawkmoth effect was introduced by Eric Thompson and Leonard Smith and is named after the butterflies kind of less popular and attractive cousin. The Hawkmoth exists within our models themselves and the rules built into them. I put a Hawkmoth into my flume on the right, and again the original is the one on the left. As we explained earlier, the rules we use in our models can only ever be simplifications of the real world, but different models will make those simplifications in different ways and to different levels of detail. They may do calculations to a different number of decimal places, or they might use a slightly different value for an important variable. Like the butterfly, those small differences that are introduced are imperceptibly small at the beginning, but the further we go into the future, they begin to expand and our models diverge. Actually, the equations that we use to represent the processes of geomorphology are highly uncertain. The technical term really is a bit crap.
What? Look, sir, confirmed.
To be fair, the processes of sediment transport are extremely complex. There are several different rules for a modeler to choose from, and they're based on different sets of observations of rivers and experiments. My Hawkmoth is switching from one set of rules to another. The danger of both the butterfly effect and the Hawkmoth effect is that even if you do use a range of initial conditions to capture the butterfly, the Hawkmoth can still fly free. The end result of this could mean that your range of possible futures could completely diverge from each other using different models. Modelers must be prepared to capture both of these bugs. And that requires us to understand our models and what they are, and crucially, what they are not capable of. So now you know how to capture the butterfly and the Hawkmoth. Now go find them in your models. If you've enjoyed this video, please do like it, and please do subscribe to my channel so you don't miss any of my future content about models and flooding. But for now, stay dry out there.